are here now at question 5. And question 5 says, Elizabeth makes $200 a week at her summer job and spends her entire weekly income on two products, on running shoes and designer jeans, because these are the only two items that provide utility to her. Furthermore, Elizabeth insists that for every pair of jeans she buys, she must also buy a pair of shoes. Without the shoes, the jeans are worthless. Therefore, she buys the same number of pair of shoes and jeans in any given week. So that's the basis of this question. And part A says, if jeans cost $20 and shoes cost $20, how many will Elizabeth buy of each? So let's target that question. We remember for every pair of shoes she buys, she also buys a pair of jeans. So therefore, if shoes is represented by S, then S must equal to J, because the number of shoes must equal to the number of jeans, because she always buys them in a fixed proportion, a 1-to-1 proportion. Income is equal to 200. The budget constraint is given by this equation, where income is equal to the price of S times, so the price of shoes times the number of shoes she buys, plus the price of jeans times the number of jeans she buys. We know the price of shoes is equal to $20, so this is equal to $20 times S, plus the price of jeans, which is $20, times J, but we know that J is equal to S. So therefore, we can just say 20 times S. So this is equal to 40S, and we know her income is 200. So we can say $200 is equal to 40 times the number of shoes or jeans that she buys. So to solve for S, we can say S is equal to 200 divided by 40, which is equal to 5. So therefore, we can say that S is equal to 5, and the number of jeans, J, is also equal to 5. So she buys 5 pairs of shoes and 5 jeans if $20 were the cost of jeans and $20 were the cost of shoes. Part B says, suppose that the price of jeans rises to $30 a pair. How many shoes and jeans will she buy? Well, we'll use the same equation from before. Her income would be spent by having the price of shoes times the number of shoes plus the price of jeans times the number of jeans. So shoes is still $20. So 20S plus, but jeans is now $30. So 30J is equal to 200. 20S, so 20 times S plus 30 times S, because we know that she buys jeans and shoes in the same proportion. 50S is equal to 200. Therefore, S is equal to 200 divided by 50, which is equal to 4. Therefore, she would buy 4 pairs of shoes and 4 jeans. Part C says, show your results by generating the budget constraint from part A and B. Also draw Elizabeth's indifferent curve. Excuse my bar drawing, but suppose this was the number of jeans and this was the number of shoes. If she had $200 to spend and she spent her entire $200 on jeans, then she would be able to buy 10 jeans. And if she spent her entire $200 on shoes, she would have been able to buy 10 shoes. So that's how we get the two endpoints. And so this would represent a budget line. We'll call this budget line A. In part B, the shoes were still $20. So therefore, if she spent her entire income on shoes, it will still be here at 10 shoes. But jeans was $30. And we know if she spent her entire income on jeans, she would have get 6 2/3, which is equal to 6.67. For part B, the budget line would have been something like this. This would be a budget line for part B. Now, they also asked us to draw the indifferent curve for Elizabeth for both part A and part B. So in part A, we saw that she would buy 5 shoes and 5 jeans to maximize her utility. So our indifference curve would have looked like an L shape, because she's buying things in a fixed proportion, a 1-to-1 proportion, and any additional jeans or any additional shoes outside of this fixed proportion is worthless and it adds no extra utility to her. So this would be utility 1, or part A, or I should just put A for consistency. And so in part B, when the jeans was $30, we saw that she would have purchased 4 jeans, 4 pairs of shoes and 4 jeans. Right, so 4 should be somewhere here. And her indifference curve for part B would have looked like this. And if you don't like my drawing, because I know it can be very bad, you can just take this graph. This is the graph that you were looking at. Part D says, to what effect, income or substitution, do you attribute the change in utility levels between part A and part B? The answer is that this change from the indifference curve for part A to the indifference curve to part B is entirely attributable to the income effect, because there's no substitution effect due to Elizabeth's insistence on a fixed proportion of jeans and shoes. Right? Because as we discussed before, any additional jeans or shoes outside of this fixed proportion doesn't add any utility to her. And in case you're wondering or you forget what are the income and substitution effect, I pulled this from the slides just for a reminder. You can pause the video and read all about it. Now, we look at Elizabeth's demand curve for jeans. First, calculate how many pairs of jeans she will choose to buy if jeans prices are $30, $20, $10, or $5. So to answer this, we know that 20s plus the price of J times the number of jeans is equal to 200. So 20s plus Pj times S, since S is equal to J, must equal to 200. You can pull the S on the outside. So S times 20 plus Pj is equal to 200. Therefore, S is equal to 200 divided by 20 plus the price of jeans. We can just substitute these values into this equation and we should get 4, 5, 6 and 2/3 and 8. Just in case you're wondering how did I get these values here, I will just do the first one to show you. So I get this 4 by substituting 30 into this equation. So it will be S is equal to 200 all over 20 plus 30, and you should get 4. Part F says, use the information from part E to graph Elizabeth's demand curve for jeans. But we'll come back to this because in a later question they would ask us to graph something else, so we'll put the both graph into one. So part G says, suppose the income rises to 300, graph a demand curve for jeans in this new situation. Then the equation that we just derived before would now be S equal J equals 300 over 20 plus the price of jeans. And if we create back our same table, price of jeans versus the number of jeans or the number of shoes, we would see, and for every price, 30, 20, 10 and 5, for every price the demand, her demand increased. It increased from 4 to 6, it increased from 5 to 7.5, it increased from 6 and 2/3 to 10, and it increased from 8 to 12. And again, in case you're wondering how we get this, I just substitute 30 as Pj into this equation. So I'll just do the first one so that you will know how to do it for each one. So 300 divided by 20 plus 30, and this should equal to 6. So you can do that for each one of these numbers here, and you would get these values. The demand increase at every price, then we know it is not a movement along the demand curve, it is a shift of the entire demand curve because the demand increase at every price. And if we were to plot price versus quantity, so if you plot the demand curve from part E and from part G, we would get these two demand curves. So this would be the demand curve from part E, the first one, and the prime, well D1, would be the demand curve from part G. So part H says, suppose the price of one shoes rises to $30 per pair. How will this affect the demand curve drawn in part B and C? Well, frankly speaking, there is no demand curve in part B or C, but I think they were referring to the demand curve that we drew in part F and part G. So how would this affect the new demand curve? Well, the equation would now be S equal J equal 200 over 30 plus the price of jeans. And if we were again to plot these values, so for 30, 20, 10 and 5, so if we substitute these values going down here into this equation, then we will get these values on this side. So I'll just do the first one again to show you. It would be 200 all over 30 plus 30, which should equal to 3.33. And you solve for all, you will get these values. And notice that these values are smaller than what we calculated in part E and part G. So therefore, this higher price of jeans would shift the demand curve inwards. And that answers this question.